Today, we're going to talk about building operational digital twin solutions in a low-code framework. This is in contrast to building such solutions in web applications or software programming. So first, a couple of slides to introduce what's a operational digital twin. A really good definition comes from Dr. Adam Rashid from AWS. Essentially, operational digital twins are used to represent both real-time and historic operations of your physical systems or assets. Those can range from a large system like a oil and gas rig or a manufacturing plant to something smaller like a single machinery. There are many benefits to having a operational digital twin on your physical system. The first one is now you have real-time visibility to how your physical system is performing, and then you can improve the efficiency of your system. For example, predictive maintenance is a popular component of a operational digital twin, and you can use that to reduce downtime. But there are many other efficiency optimization you can do. For example, you can also use it to improve the utilization of your system or assets to achieve better efficiency. You can achieve cost reduction. If you monitor the lifetime of each component in your system and understand when they need to be replaced, typically you can replace them later than if you were replacing them without understanding of your lifetime of your components. You can perform trend analysis. So you can look at the historic data to understand how your system is performing and where you can optimize them. And finally, you can improve the performance of your personnels, whether they're IT teams or they are field teams. You can give instructions to them as to how to enable them to run your systems better. This slide shows a architecture of a operational digital twin solution. It is actually fairly simple from an architecture perspective. So first at the bottom, you have the physical data sources. They can come from sensors, they can come from machines, they can come from controllers or log files or even video cameras. And they typically can come directly from the physical equipment, or they can come from databases like Snowflake or Pi, or they can come from software APIs. So there's a variety of different type of data sources, data formats, and storage for the source data. Now you have to be able to take that source data and process it in something called a data engine in order to extract the insights you need to be displayed. And the insights are typically stored in a database or data warehouse. We call it a data layer. And you would have something called an event data layer if it's an events that you extract from your raw data. And finally, at the top, you have a visualization layer. That's essentially a dashboard or something cooler like a 3D thing for you to display trends, work instructions for your personnel to consume. Now let's go into how this digital twin solutions are implemented. It obviously makes sense for pretty much every physical system to have a digital twin because the digital twin can really improve the efficiency of the physical system enormously. However, today's methods of implementing digital twin is very slow, it's very expensive, and it is difficult to support by internal teams, right? Because basically it's a black box for the internal team. And also it is very slow to evolve. And unfortunately, all systems evolve really fast these days. So without the ability to evolve fast, systems kind of get out of date very quickly. The reason for that is because when we look at how the solutions are implemented, they come from sort of the software programming methodology, right? So visualization is typically implemented in a web application. Maybe it's based on a digital twin framework, but there's a lot of coding for the front end, for the back end. Similarly, for the data engine, there's a lot of code development, right? Maybe you'll require programmers to use Python to build the data engine. And it gets very complicated when you have many, many data sources and when you have to perform sophisticated data analysis. So this whole process is very difficult and it's very time consuming. And this is why it is difficult to build such a digital twin with today's technology. So at Prescient, we have been experimenting with low code implementation for a long time. So every single tool we use is based on the low code principle, right? So from the visualization layer, we use Grafana, which allows you to drag and drop dashboard elements. And the data layer, we typically use InfluxDB because it's a very good time series database and allows very fast query of time series data. And at the data engine layer, we use what's called functional block programming. That's essentially drag and drop type of programming. So when you combine these three low-code elements together, you can implement digital twin solutions really fast. For example, in our experiences, it typically takes a couple months to do, but keep in mind that we have the skill. For your own internal engineers, it may take longer, but it's still significantly faster than building this in programming. And the cost is a lot lower, right? So it's almost 10 times faster, 10 times lower cost. And it's very easy to support because as you see, these software tools, are very easy to use by engineers, which also means that it's fast to evolve because making feature changes takes days, not months, like what you do in programming. So let's first look at the data engine component, which is probably the most important component because the quality of the insights depends on the data engine. So Node-RED is a graphical programming language, and it's based on blocks, right? It's hierarchical. What it means that you can have a block at the top level, and you double click, you can descend into it, and there you have this data flow that has many blocks, drag and drop blocks, and they can, get data from the source. They can analyze the data to produce events, and you can double click again to go into this block, and that shows you the data validation block, the event generation block. So by having this visual graphical methodology, it's very easy for engineers and even non-engineers to understand. It's very easy to contain the complexity as you grow in your solution. There's a lot of existing modules available, so you can leverage on what other people have done, and you can embed very sophisticated analytics, including machine learning models, into Node-RED, so that essentially gives you ability to go as deep as you like in terms of doing data analytics. Now, InfluxDB is one of our favorite databases, although in this case, we've also used other type of databases or data lakes to be the data layer. But InfluxDB has multiple huge advantages, right? For example, when it comes to time series data, which is, the most common data type when it comes to operational data, InfluxDB is very fast. Queries run very fast. Data lookup run very fast. And compared to a typical data lake, it is much faster. And InfluxDB is not super light, but it's light enough that we can deploy it in the cloud or as a container at the edge. So that makes it flexible as to where you wanted to store the data. And then you can synchronize the data, among the different locations. When it comes to visualization, we find Grafana to be a very good tool. Grafana has a rich set of visualization types, from charts to tables to text, and you pretty much have everything you need there. Grafana also integrates very well with InfluxDB, which is not the case for a lot of BI type of software. So that's another advantage of Grafana. And finally, a lot of people today use Grafana for real-time data visualization. But Grafana is also very powerful to do batch data analysis. For example, you can run InfluxDB queries in it so that you can, get batch, type of data results, which is very important for digital twins, because digital twins are not just real-time monitoring. There's a lot of historic analysis you do to really understand the performance of your system. So while Node-RED, InfluxDB, Grafana are very, very powerful already, what we have found is that there are certain enhancements that make them much more powerful. So in this case, when it comes to Node-RED, one of the challenges is that data typically are located in different places. Some of them are in the cloud, some of them are at the edge. Therefore, a distributed Node-RED is needed. Imagine if each of this data engine symbol is a Node-RED. You really wanted to be able to deploy this data engines to different locations to collect the data, analyze the data, combine the data together to generate events. So, we have modified Node-RED so that we can basically drag and drop this data engines and put them wherever they are needed to process data. And we also have added many data processing modules, like different type of data connectors, data validation blocks, data transformation blocks, and different analytics blocks. So, as you build up your modules library, it becomes easier for you to build data solutions. On the Grafana side, the biggest challenge really is the fact that Grafana does not have interactive capability. Grafana mainly is a dashboard, right? So it's for view. But very often we wanted to integrate the view functionality with interactive forms, buttons, so that users can interact with the dashboard. So in those cases, we can use some external modules, but a lot of times we add custom JavaScript into it. So essentially, we can build whatever we want inside Grafana now, and that becomes very powerful. Another addition is using an API to link Grafana and Node-RED together. This is because as soon as you start to have interactive components inside Grafana, you need APIs to send the user inputs to something to process the commands, right? And that something is perfectly done by Node-RED. So we have built APIs to link these two pieces together. Then all of a sudden you can execute very complex user instructions from Grafana sent to Node-RED, and then Node-RED does all the processing. So this is one thing that we find to be very, very useful. Whether it's the instructions from the users or it's the data source, I mean, you need a data engine to really do all these things. So finally, what we have discovered is that this low-code framework enables fast implementation, reduced cost, internal support, and ultimately, what's important is that it enables continuous innovation without having to invest into huge software teams, huge and expensive software teams. And as we have shown, we have found that building a low-code digital twin solution is so much faster. Imagine, not 10 times faster, but 2 times faster. Imagine you could be 2 times faster every year. You would have a huge advantage, right, in 5 years. So I think that's what low-code offers. And we would love to hear your feedback. So please leave a note in the channel if you have any thoughts. Thank you.